All right, Stephen, how are you doing?
I'm doing great, Charles. How are you?
Great. So we're with Stephen Toub again. Last time we talked, it was all about async.
Yep.
Remember?
I do.
PDC 10, and you were on Channel 9 Live, and you gave us a beautiful explanation of the TPL side of the house, which is part of that equation. One of the things we touched on very briefly was TDF, or Tasks.Dataflow, and I want TPL Dataflow, and I wanted to come to you and really dig in a little deeper to what that is, what that means, what's going on.
Awesome.
So what's happening?
So, as you said, we talked about this a little bit, and it has a lot of tie-ins with the async stuff as well, so we'll bring that in.
Perfect.
But in .NET 4, we really did a few things. We introduced this new task type, which is sort of a fundamental unit of concurrency or asynchrony, whatever you want to talk about, however you want to describe it. And then a set of higher-level primitives or constructs or algorithms, whatever you want to call them, for using task to do more complicated parallel processing. So if you look at Parallel 4's implementation, it's built on top of tasks. If you look at Parallel Link's implementation, it's built on top of tasks. And that's really using this core task primitive to solve certain kinds of parallel processing problems. And we bit off a fair number of them with Parallel 4, Parallel for each, Parallel Invoke, Parallel Link, and so on. But there's also a certain set of problems that we addressed, but only by providing the fundamental building blocks rather than by actually providing a complete solution for that area. And that area is really what TPL Dataflow is meant to address. It sort of sits at the same level as parallel loops and parallel link and so on to provide another parallel programming model for solving another large set of problems.
Okay.
Again, all built on top of tasks and concurrent collections and other things we've done, but providing for problems that weren't easily addressed with parallel loops or parallel link, another set of APIs to bite off these kinds of problems.
So then the quick question I would ask is, what are those types of problems? I mean, clearly it's analyzing large data sets, data flows. I mean, explain.
Yeah, it's more the latter of what you said. It's more about kind of the patterns of problems that you would otherwise, you would try to address. So with parallel loops, the pattern is really about fork join, right? I've got a set of data to analyze, and it's sitting there, and I'm going to spin up a bunch of tasks, fork them off, and join back together.
Yeah.
And obviously the implementation tries to do some sophisticated things to minimize overhead, but at its simplest form, it's in fact fork off a task for each operation and join back together. We provided some primitives for doing things like producer-consumer problems, but really more in a kind of synchronous or blocking fashion. So we introduced a type called blocking collection, which allows producers to push data into this collection to say add, 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 and for consumers to say take, take, take. But when they say take and there's nothing there, they sit there blocking until more data is available, which is great for certain kinds of these producer-consumer situations where you have a dedicated set of threads that you want specific for this consumption purpose. Likely it's the only thing this application is doing is taking data from somewhere, just sitting waiting for more data and processing it. And it's okay then to block because you've got a few threads and their whole purpose in life is to consume from these pipelines. But there's another much larger set of producer-consumer related problems that really focus on async, where the synchronous blocking isn't appropriate. And at a very 30,000-foot level, you could think of the Dataflow library as being all about these asynchronous producer-consumer problems in a large variety of flavors. But it's really about someone sending off a message and then going on and doing their stuff, and someone else doing other things, getting notified that a message has arrived, processing the message, and then going back to doing other things. And the library, both on its own and then in concert with the async language support in C# and Visual Basic, provides different ways to address those kinds of problems in kind of whichever style most suits the developer.
Excellent.
So at a high level, it's these producer-consumer problems, which you can also think of as encapsulating I'm probably going to get in trouble here with some purists, but encapsulating another set of problems which are more around structuring your application or your architecture to be more kind of in an actor or agent model, where I have a bunch of individual entities that are themselves kind of either running sequentially or potentially themselves has some concurrency built into them, some parallelism built into them, but they're communicating with everyone else in the world by producing messages, by sending messages that other folks then consume, process, and potentially send other messages in return. And these actor or agent-oriented architectures often end up scaling a lot better than taking a parallel for loop and trying to run it over a million cores, right?
Yes.
Especially not only because there aren't as many problems that scale to that capacity,
Sure.
but also because you start having a lot of synchronization at that level of scale. And it's much easier for us as humans and software developers to think about, I'm going to have this small, maybe 4-core, a thing that can possibly scale to 4 cores running as an individual agent over here, and this guy running sequentially over here, taking up at most 1 core, maybe I have 1,000 of those, and they're all communicating. And so because they're all running independently, they can all run concurrently, and you can scale up to however many cores, agents you have to run on your cores. But you don't have to think globally in terms of what they're all doing at the same time. You just get to think about an individual agent and how it deals with the messages that are coming into it and how it deals with the messages it's sending out.
Excellent. So coordination is sort of the magic sauce, right?
Right. And I would say it's about coordinating these messages. It's about buffering these messages, because if you process a message as soon as it arrives and you don't allow other messages to come in until you're done processing that message, then you're blocking whoever's trying to send you the message. So by definition, you need to be able to buffer data, or tell someone who's sending, you know what, I'm going to call you back in some fashion. When I'm ready to accept more data, you can go on about doing other things, and then I'll let you know when you can try again.
Excellent.
Propagate to me. So the library provides the fundamental building blocks to build those kinds of systems. It doesn't provide a full language or a full set of libraries around building up actors or agents. There are a lot of other languages or libraries, like Erlang, for example, that's focused entirely on this kind of model of processing. What TPL Dataflow library really provides is the ability to design your own systems that utilize those kinds of capabilities, but you end up creating your own infrastructure, around the primitives that we've provided.
Excellent. Now, of course, you guys are also the Axum people.
Right.
And we haven't come back and talked to you about that for ages. Don't know the status of it, but
it's still up on the DevLab site. People are still trying it out and downloading the bits and giving us feedback. And a lot of that feedback has actually influenced both the TPL Dataflow library and the C# VB async support, in terms of the kinds of things that people want to be able to do. And there are a variety of things that Axum provides. A good chunk of them are covered by what we've taken from the language and put into this public library, and what we've taken from Axum and put into C# Visual Basic in terms of the async support.
Perfect. And before we get you on the whiteboard, I wanted to quickly address the notion of RX and TDF better together versus being sort of these two things that do the same thing, choose your poison. And you mentioned this in the paper that you wrote that comes along, the documentation that you wrote that comes along with the bits.
Right.
And you said for the astute reader, RX, you might be thinking, what about RX? And of course, even on your excellent screencast, by the way, on Channel 9, the first thing one of the Niners asked was, this seems a lot like RX, or maybe it's not, or I don't know. And
I should go back and look at the comments. I haven't looked at them in a while. Sorry, whoever that was, I'll answer
Sure,
you.
totally. That was Al, by the way.
Sorry, Al. At a high level, because it's all about kind of data moving around the system, it's very easy to think of them being the same kind of thing. And at the 30,000 foot level, they may look that way. But when it gets down to the nuts and bolts, you would really often, one of them will be more appropriate for the problems you're dealing with. There are a lot of things that RX provides that TPL Dataflow does not and was never intended to, and vice versa. Yeah. RX is phenomenal for being able to coordinate these push data streams that are just kind of moving through, and how do you write very complicated logic in a concise set of link queries to process these streams of data. And that's its wheelhouse. Excuse me. TPL Dataflow is more about these fundamental building blocks for building up these kinds of actor or agent systems, where you need to have control over how you buffer your data, where you need to have control over how you process and consume that data, where it's not necessarily just a push model, but also okay, you're trying to send me data, but I'm not ready for it yet. I'll come back to you and I'll get it from you. Or I'll come back to you and I'll get it atomically from multiple sources so that I don't deadlock a system. For doing non-greedy joins across arbitrary sources, for having consumers where maybe they're processing 4 or 8 or 12 things at a time, but they're not buffering data. They're going back to the original source to say, okay, now I need more data to process. If you have some more, give it to me. Otherwise, send it to me later, and I'll spin up again, and I'll continue processing. So it's really much more focused on a more imperative style of programming. It's more focused on where the data lives rather than how you coordinate individual messages as they're propagating through the system. And I think from my experience using RX versus using TPL Dataflow, there are places where I'd say, I don't want to use TPL Dataflow, I'm going to use RX here. And there are places where I'd say, I don't want to use RX here, I'm going to use TPL Dataflow. You could probably solve any problem using either, but you're going to end up writing a lot more code in various cases to deal with it. And so it's, I'm not one of those folks that likes to provide a huge number of options that are all overlapping and telling people, go try them all and pick whichever one suits you. But in this case, I think they're distinct enough that you'll naturally find yourself choosing one or the other. Which brings us to the better together story. It doesn't have to be either or. We've already seen some customers who will use TPL Dataflow to implement certain parts of their system, but then for certain cases where they don't need the richness around the buffering and the control, but they instead want to be able to take multiple streams that are emerging from their Dataflow blocks and manipulate them in some fashion, they'll then start using RX to take those data streams, coordinate them, and then go back to using Dataflow blocks for certain other parts of the system. And that's really the kind of thing that we imagine happening. So it's very easy to take data and post it to your subjects to be consumed through your observables, or to take your observable stream and subscribe observers or actions that then post to your Dataflow blocks to have the data buffered and the like. It's pretty easy to go in both directions.
Excellent. And one last thing in terms of the native people, that is the C++ programmers, the C programmers. You guys introduced the CRT in 2010, .NET 4, well, God, excuse me for saying .NET 4, 2010, Visual C++, 2010, and asynchronous agents, the asynchronous agents library. Where do those guys fit into this beautiful model?
So if someone's familiar with asynchronous agents, TPL Dataflow will look extremely familiar. At a high level, the concepts are all very much the same. Some of the things are named the same. A lot of them will sound like they're synonyms, for the naming, where we chose certain namings based on the .NET framework naming conventions versus naming based on CRT, or C++ naming conventions.
Okay.
For example, asynchronous agents has a thing called call of T. We couldn't use call because we wanted something slightly more descriptive, like the .NET framework typically goes for,
Sure.
and B, it's a reserved keyword in Visual Basic, so anyone who wanted to use that would need to wrap it in the in the angle brackets, or in the brackets. But a lot of the concepts are similar. There are some features that differ. As we've often done with our managed side of things, we've tried to build in kind of a slightly richer set of APIs to address common needs, whereas on the native side, you end up building some of that yourself. So for example, I'm maybe getting a little ahead of myself, but on the managed side, we allow you to basically mark a block as not having any more data coming to it, and then the block can shut itself down.
Nice.
Whereas on the native side, you have to kind of build that functionality yourself. But for the most part, the libraries have the same kinds of Dataflow blocks built into them. They allow for the same kinds of patterns, and they're very similar. We do have a few extra things in the managed side as well to integrate nicely with the language support.
Excellent. And of course, just to make this clear, you're targeting a different audiences. As Bjarne Straustrup says, the concurrency problem has been the biggest thing for the past 50 years, right? The next big thing. And C++ has always had facilities in it to make it easy to write. Not easy, but successfully
to assist,
compose threaded programming.
Right.
So that's good to know. Right on. So, just so people know, you're an architect now. And so congratulations, first of all, because that's awesome. You actually implemented a lot of the async stuff on the TPL side. Mm-hmm. And so as an architect, whiteboard, which you're always great at, maybe you could draw out for us how TDF actually looks from the architectural side, and then we can dig into the fun stuff.
So it's a very componentized system, and this is where things will look a little bit like RX. I'm not going to draw the same kind of diagrams that Wes and Eric and so forth do. I'll focus more on how the data types themselves are structured, because again, it's all about how data is buffered and how it flows, and therefore it's more on where is the data stored rather than how does the data kind of propagate.
Sure.
Or when does the data propagate. So I think I'll start by just describing one of the simplest, what we call data flow blocks, and show how you might build this yourself on top of what's there in the .NET Framework 4, and then how this wraps up a lot of that functionality for you. Okay, so let's say you were in a situation where you had a producer thread who was going to be sending some data, and that data needed to be buffered up in some fashion.
Okay.
And then you have one or more consumer threads, let's just say for now actually that we just have one, who when data arrives wants to process as much data as is there.
Okay.
And then when no more data is there, he'll go away. And that way he's not tying up any threads when there's nothing to be done, only when more data arrives would he spin up. So what you might do is you might have a concurrent collection. So let's say maybe you'd have a concurrent queue of whatever your data is. And when a producer adds data, he might kind of do, enqueue that data into the collection, and then set some kind of flag, data available, let's just say, if no task running, launch task. And this task would be this consumer task up here that's going to spin up and start processing. So then this task that's running is going to sit in the while loop, while basically the concurrent queue dot try dequeue. So while it's able to grab another piece of data, it'll process that data, and then when it's ready to go away, it'll go away, and there's no longer a task running. So if this guy quickly queues up 5 pieces of data, the first one's going to get enqueued, and there won't be a task running, so a task will be launched.
Okay.
And then when more data arrives, let's say this guy hasn't yet completely spun up yet, that data will get enqueued and a task will be running, it's been launched, or task queued, I guess we could say, queued or running, in which case the data will just be added. Meanwhile, this guy finally gets spun up, he starts processing, he dequeues the first item, the next item, the next item, and so on. If this guy keeps pushing in data, this guy will keep finding data available. But as soon as there's no more data to be processed, this try dequeue will return nothing, and then he'll exit. And then the next time data gets produced, we'll enqueue it, and we'll launch a new task.
Okay.
Right? So all of this logic, you can imagine this getting slightly more complicated as well. Rather than whether you want a single task running for a single consumer, you could imagine having some number of tasks, so 4, and then this is task queued or running. This is less than or equal to, or is less than 4 tasks currently running.
Okay.
If not, spin up a new one. So you start getting some parallelism by having multiple tasks that are able to consume. And all of the logic that I basically described here can be built easily on top of the public surface area from .NET 4,
Okay.
with tasks and concurrent collections and so on. But one of the fundamental types that we have in TPL Dataflow is this block called action block. Which takes all this functionality and just builds it in.
Nice.
So when you call .post with your data element, that's effectively this logic here. You're enqueuing the data, and you're potentially spinning up a task if one isn't already running. When you construct this, you give it a action of t. And again, I'm just talking about the very simplistic usage. There's more to this.
Sure.
And then this task that gets spun up, for every item that it dequeues, it runs that action. Right? So kind of a very simple progression from the kind of code you'd have to write to do this kind of thing manually to it's just encapsulated into this action block. So the action block is this very cheap little data structure that contains this logic, that contains a queue, that contains a count of the number of tasks that are active, some options and things like that. which allow you to very easily offload work elsewhere. Right? I have some processing to be done. I'm going to have data coming in. Just create one of these action blocks, and every time I get any piece of data, just pass it off to it, and it'll handle processing that data as fast as it can with as many tasks as you allow it to have, while not creating a whole lot of garbage in the process. The only real allocations that are happening here are whatever allocations are necessary as part of this queue data structure, and whatever allocations are necessary for the tasks itself to spin themselves up. But because we reuse the tasks, as long as you have data coming in, you're just using the same tasks, and you're not allocating per message, you're not doing any of that kind of stuff. So you get this very efficient processing mechanism. So now you can take a block like this and you can use it in a few ways.
Okay.
And we'll come back to some of the other features that are in this action block. But one way you can use this is, now imagine I have an object. I have a class. Let's call this, one of our samples in the async CTP is a real estate simulation.
Okay.
So let's say that this is a realtor agent. Okay. And so this realtor agent is its own entity, it's a person or whatever, and he's going to be receiving messages from buyers that are interested in buying something, right? So a very easy way this realtor may have some shared state in here, right? Because it's an object. It's like kind of object-oriented meets concurrency.
Nice.
And he's going to be receiving in some messages which he needs to process and which may manipulate this shared state. And then maybe he'll be sending some messages back out. So a very easy way to deal with this is he can create one of these action blocks for processing a particular type of message. And then anytime one of these messages comes in, which may just be a function call like buy, this buy function can just post that request into the action block to be processed asynchronously. And by default, this action block just has one task, which means that if this is the only action block in this whole realtor agent, it's able to access this state without taking any kinds of locks, because it's a sequential process, even though it's asynchronous, and it may be spinning up different tasks over different periods of time. There's only ever one active at a time, so it can easily access this shared state without having to lock on anything or so on. But now let's say that this realtor agent had a bunch of different kinds of messages coming in, and maybe there are multiple action blocks here. And each one of these may be potentially accessing the shared state. So even if these are all processing sequentially, they might be receiving multiple messages at the same time, and I'll be trying to access the shared state. So folks that are familiar with the CCR, the concurrent sync coordination runtime, may be familiar with a construct from the CCR called interleave. Or if you're familiar with any of the writings of Jeffrey Richter, he has a type called reader-writer gate, which I think is part of his concurrency library. These all work on all in the same kind of principle of basically having the equivalent of a reader-writer lock, where certain things, you can have multiple things accessing state as long as they say they're only reading, but you can only have one thing accessing the state if it says it's writing. With these asynchronous counterparts, interleave or Richter's reader-writer gate, or what I'm about to mention here, you have the concept of having things queued up, and each of those queued up items has associated with it, in effect, an annotation about whether it's going to be concurrent, or a reader, or exclusive, a writer. And then those things only get scheduled when they're able to do their job. So if there are only concurrent things that are queued up, they can all be scheduled at the same time because they're only reading. But as soon as an exclusive thing arrives, we have to wait for all the concurrent things to stop, then the exclusive thing can be queued, and only once that exclusive thing is done can we either schedule more exclusive things, or one at a time, or schedule all of our readers. So there's another type in the Dataflow library called concurrent exclusive scheduler pair. It's a long name, I know, but it's descriptive.
Yes, it is.
And if you're, again, this shows how we're building on top of and using things from the task parallel library from .NET 4. This type is very simple type that exposes, from an API service, that exposes a concurrent scheduler and an exclusive scheduler. both of which are just .NET 4 task schedulers.
Okay.
So you can just schedule a task to these guys, and they'll behave exactly like I just described. This is basically serving as the coordination mechanism. Any tasks that's scheduled here are in fact readers, and they can all run concurrently as long as there's no exclusive task queued up. But as soon as there's an exclusive task, only one exclusive task can run it at the same time, and no concurrent task can be running at the same time. And this guy manages all of that.
Nice.
So how does that tie in with this? Well, as I mentioned, the action block under the covers is queuing up these tasks. Mm-hmm. So one of the configuration things you can do with an action block is tell it where you want it to schedule its tasks. By default, these tasks are just running on task scheduler .default, which is the .NET thread pool. But you can point them to run wherever you want. So if, for example, we have this buy method, and let's say we also have a query method. So our buy is going to modify state in the realtor because it has to update its tables on what properties are currently available, which ones have been bought, and so on. So we may configure this guy to use the exclusive scheduler.
Okay.
Whereas query, we can have servicing many queries at the same time, asking what kind of properties you have available and so on, so we can configure that guy to run on the concurrent scheduler. And now, these can both access this shared state without taking any kind of locks. We just create our delegates here, and the delegates, when they process the tasks to process messages here, will only run when there's no concurrent tasks running. They'll only run one at a time, but if there are no more of these guys can all process with whatever degree of parallelism we've kind of told the system through another set of parameters to the action block about how much concurrency you want at the same time.
Nice.
So you can encapsulate, and that's really one of the intended usages, encapsulating these blocks into your objects so that you can process data in whatever internal manner you want without having to write all this kind of complicated logic, which a lot of people end up writing today to handle themselves.
Very nice.
So that's one way that this action block can be used, or kind of one architecture. I'm going to put action block aside for a sec and talk about some of the other blocks, and then we'll come back to other ways that this block can be used.
Okay. So which one do you want to erase? This one?
I'll erase this one.
This one's fine, because that's just the...
All right.
Okay.
So, and this next piece is where it's going to start looking a little bit like RX from the high level.
Okay.
Okay. So you can see that this block here, action block, takes an action, so the action shows up here, but we have this word at the end here called block. And this isn't the only type in the Dataflow library where block shows up. There's about 11 different types that have block in the name, or classes that have block in the name. Basically, a block is any of these entities we have that may have some number of inputs for receiving data and the ability to kind of output data.
Okay.
So another kind of one of the simplest blocks from a understanding perspective is one called buffer block. And if you're familiar with the CCR, buffer block is the closest equivalent you would find to the port type in CCR. Really, you can think of this as, again, kind of a thread-safe queue with various kinds of logic around it for doing certain things. But it's basically a queue that you can put data into asynchronously and get data out of asynchronously.
Perfect. And just for the native people, it would be the unbounded buffer.
Exactly.
For C++ and CRT and async agents. You've got
Exactly.
to keep mentioning my C++ people.
No, it's great, and I should thank you for reminding me because it's good to draw those parallels. No pun intended.
I do find it odd. I just have to say that the block is so widely used, which that is essentially the B word.
Yeah,
for,
it's a different meaning of the B word.
All right.
It's actually a good point.
Yeah.
It's a thing.
Got it. Yes.
A block.
Yeah.
And I love Lego, so it's like a little Lego block or
totally. It makes sense.
Yeah,
it makes sense.
Okay, so let's say you have one of these buffers. Now you can use one of these buffers in a producer-consumer scenario, right? In a synchronous producer-consumer scenario, I can have a producer coming along and calling post to put data into the buffer, and I can have a receiver, a consumer come along and call receive to pull data out of the buffer.
Okay.
And this receive call, which is kind of being called here, is going to block, or is going to wait until there's some data to take. And so in effect, just using these two APIs is very much like using a blocking collection with add and take. It's kind of like post and receive. Not identical, but similar. However, this isn't really the most common way that you would use a buffer block. We provide these APIs like receive in case you do want to block waiting for data to come out. But a more common usage would, instead of being receive, would be to use receive async. So where receive returns a T, if this is a buffer block of T, receive async is going to return a task of T using the task type, which then ties in very nicely with the C# and VB async functionality. Yeah. So if I have a consumer that's just going to be sitting in a loop, receive async, and then process, I should say await.
Yes.
Process next item. So now, when he calls receive async, he's getting back a task that represents data that's already been received, or the kind of future promise that data will be available. And at that point, if this task hasn't yet completed with the data, this await here will tell the compiler, the asynchronous method, to basically suspend the processing of this method and give back the thread until the data is available. So now I have an asynchronous consumer here that's pulling from this buffer block. And now I can very easily write these asynchronous producer-consumer scenarios with, again, a single block where I want to kind of write my imperative logic for processing data with my while loops and my for loops and my conditionals and whatever else. But it still gets to be asynchronous in nature.
Nice.
So that's one way you might use a buffer block. Another way is to actually link these blocks together. And now we'll kind of come back to action block.
Okay.
So if I have a buffer block with its queue of data, and I have an action block with its queue of data and some tasks here for processing and so on. Rather than posting directly to my action block, I can use a method called linkTo to basically say, rather than forcing to someone to explicitly come to this block to get data, anytime you have data available, automatically propagate it to a block that you're linked to. Excuse me. And you could be linked to any number of these guys. Excuse me. So you can have basically this fan out where a single block can be linked to multiple targets. And you can also, if I had multiple buffer blocks, I can have this, multiple targets, multiple sources linked to the same target. And what happens then is, just like when we call receive async, and this task completes when data becomes available, that's happening with the buffer block basically notifying anyone who's listening over here, hey, new data is available. In the case of receive async, it's pushing data into the task that was previously returned. In the case of being linked up to an action block, it's basically offering the data over to the action block to be received. Okay. And with the kind of the defaults, if I do this, all the data as soon as it enters here is going to be propagated out to the action block. And that's going to happen asynchronously as well. This propagation happens by the buffer block, again, spinning up a task to propagate the data, and this task goes away when there's no more data to be propagated. But again, there's further configuration that can be done here. So let's say, we're going to go back over here and erase this.
Perfect.
Let's say you were in a situation where you wanted a bunch of different processing to happen with different action blocks. Maybe I have 4 of these guys. They may all be configured to do the same processing. They may all be configured to do different processing. But with this configuration, if I have a buffer block, I can in effect link the buffer block to all these action blocks. Now by default, the way this propagation works is, because we're dealing with a message-based system, we only want to send a given message to a single recipient unless we're very explicitly stating otherwise, because otherwise multiple consumers could be working on the same data and you end up with data races and things like that. So by default, this data that's offered from the buffer block gets offered in turn to all the targets. So he says, would you like this? Would you like this? Would you like this? Would you like this? If any one of them says yes, that data is removed from here, is transferred over, and no one else gets offered.
Okay.
So in this case, by default, based on what I just described, all of the data that comes in here is going to go to this first action block, because it's going to accept everything. It's just going to take everything, add it to its internal buffer, and we've lost potential parallelism. But I can configure these action blocks to be, in effect, say non-greedy. So what I just described is kind of greedy behavior.
Yes.
Do you want it? Yes, give it to me. We can configure it to be non-greedy, where the action block is going to say, you know what, I'm currently processing data, so I don't want this right now. But I'll tell you what, I'll call you back when I'm done processing my current data, and if you still have it available, then I'll take it. So in that case, let's say we start off where no one's processing anything. Data arrives here. It gets propagated up to this action block. It says, do you want it? Action block says, hell yeah. Spins up a task and starts processing that data.
Okay.
Another message comes in, gets offered up to this guy, do you want it? Well, no, I'm currently processing, so talk to me later. In which case the buffer block says, okay, how about you? You want it? Absolutely. So he takes it and starts processing. So as messages arrive, in effect you end up load balancing over all these.
Excellent.
So now another message arrives, and the buffer block says, do you want it? No. Do you want it? No. 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 He just keeps it. If someone else were to come along and call receive async, that guy would get it. Or if one of these guys finishes processing his data, now he says, I know that you offered me a message. Do you still have it? And if this guy says yes, because no one else took it or received it, then the data will be offered over and consumed, and this guy can keep processing.
And the arrows are messages.
The hours are messages.
Let me ask one quick question.
Yeah, please.
So, because I don't know if you actually said this yet, but couldn't you just take the action block and say, this action block has a queue of 1, and that's it? So in other words, I decide how much I want to queue.
Mm-hmm.
In other words, there has to be, you're about to explain how I programmatically say, only accept one job at a time.
Yep.
And then, so what's the program?
So that's a great analogy, and in effect that was initially a route we went down, is what if we allowed you to replace, or to set configurable limits in effect on this input queue, right? Which would do, with what I just described, would basically do the same thing. It would be slightly different because while this guy was processing, he would have removed the data from his queue, so he would have one slot left in his one element queue, and he would greedily take the next item even while processing the previous.
I see.
But even with that, it still would generally give you load balancing.
Sure, sure.
But now let's take a different scenario. Let's take a scenario where, let's say you're processing image frames coming off of a camera. Okay, and it takes you maybe a second to process each frame, but the frames are coming in at 30 frames per second. So what we, instead of if we were to buffer all those frames up, whether we were buffering them up here or buffering them up here, we're going to very quickly get behind in our processing. We're going to be showing you a frame every second, but we're going to be buffering up a second's worth, and then 2 seconds worth, and then 3 seconds worth of data in our buffer, and very quickly we'll be showing you scenes from an hour ago. When that may be what you want if you were going to be writing this all to a file, but if you were going to be showing kind of a real-time feed, you want to see the most recent frame rather than the oldest frame. And in a case like that, you wouldn't actually want to kind of have a buffer either here or here that stores everything. You would want something that would offer the message, but if it couldn't be taken, drop it. And then the next time you come back, you can pick up whatever's latest. So there's another block that's not buffer block, but called broadcast block, which does exactly that. Basically, it broadcasts a message to everyone, and if no one wants it and new data comes in, it'll just overwrite the old data with the new data. So now imagine that we did have a queue in here where you could configure the size. Well, now you'd also want to be able to configure things like, I want that kind of broadcasting behavior built in. You know, I want to be able to drop messages and only retain the latest or only retain the newest or whatever. But instead, by adding the non-greedy capability to this, we effectively remove this buffer from action block and allow you to put any buffer you want, either ones that we ship in the box or ones that you build, in front of the action block. So in effect, you're replacing whatever queue is inside of the action block just by putting your own custom processing logic in front of it.
Excellent.
Effectively giving you the same thing, but we, in the box we ship broadcast block and buffer block and join blocks and all these kinds of things. You can put those all before and then not have to worry about any internal buffering that's happening.
Excellent.
It's a great question, though.
So now implementing your own blocks, since you use the Lego analogy, usually with Legos you don't get to build your own individual blocks, but in this case you can. What interfaces do I have to implement?
So there's 3 core interfaces in the library, and I should say our hope is that most folks don't have to implement their own blocks.
Fair enough.
But we do make it possible. You can. Our goal would be that we ship the most common ones and we cover the 90% scenario. I'm sure some people will need to, and that's great, and we want to make that possible. I won't say in all cases we've made it particularly easy, which is something I'd like to see us address moving forward.
Sure.
But we focus more on getting kind of the majority cases correct.
Excellent.
So there's a few core interfaces. There's one called iDataflow block, which doesn't have much on it. Right now, it just has on it a property called completion task, which is, I mentioned briefly earlier that you can tell a block you're not going to get any more data, so shut yourself down. Well, once it's shut down, you might want to know that. So there's a task that hangs off of every block that in effect represents the life cycle of the block.
Okay.
So I could say, for example, if I have some action block, I could say action block.post 1, action block.post 2, do that a bunch of times, and then say action block decline permanently. And we're still debating the name here, but basically you're not going to get any more data coming in. And then I could say, if I was using the async support, await ab.completion task. And now I will asynchronously wait for all the data that I previously queued up to be processed. The block finishes processing all that data asynchronously, shuts itself down, and then I'll continue executing. Further, if any exceptions occur while processing in these blocks and you don't handle them, the block will also, as soon as possible, shut itself down, store those exceptions onto the completion task. So if I do this, the exceptions that occurred will propagate out of that await call.
Excellent.
So that's kind of the core interface, and then there's 2 other interfaces. There's iTarget block of T input and iSource block of T output. And we're currently working through a few minor changes to these interfaces to add things like and contravariance, which has been one of the top requests.
Excellent.
So hopefully that happens. But in short, basically anything that you can send data to is a target block, and anything that you can receive data from is a source block. Target block exposes interface methods like decline permanently and offer message. So I can kind of offer you message, and there's a protocol built in about, I'm offering you this message, what if you don't want it, what do you return to me, when do I force you to come back to me to get the data, or when do I just allow you to take it and tell me you took it, things like that. Source block is a little bit more complicated, so it's pretty easy to implement this. It's a little bit more complicated to implement this if you care about supporting all of the scenarios that blocks support. You don't have to. But the primary methods on here are link to, which we already saw here. This is what allows you to connect up 2 blocks.
Okay.
There's a method called consume message, one called reserve message, and one called release message. So we'll describe these in turn. Link to is just about basically telling a source block, hey, you've got another target you're going to be propagating to. That's very straightforward. Consume message shows up in these cases where the block isn't just sending the data and saying, take it if you want it and just let me know whether you took it. It's used for the case where, let's say we did configure this action block to be non-greedy. When we send a message up here, this action block stores the last message that every source offered it. And at some point later, when this task goes away, it'll say, remember that message you offered to me? I want to consume it. So it calls back to the source to say, now give me that message if you can, or let me know that I couldn't get it and I'll be okay. So that's one way consume message can be used. It's a block can remember a previous message that was offered to it, and then out of the blue just call back to a source to say, give this to me now if you can. Another way it can be used is with a block like broadcast block. So let's say that the data that I'm storing here is an image file.
Okay.
And let's say that in broadcast we allow the same message, one of the few blocks where we allow the same message to be sent out to everyone. Whereas with buffer block, it just sends it to one at a time. But now, if I'm sending the same data to everyone, and all of them start partying on that data, they can end up with race conditions. So one of the things that broadcast does by default is you give it a cloning function for your T. Basically, you give it a func of T to T, which it basically makes a copy of the data before it sends it to everyone. Now your func could just be the identity function, right? You could just do I to I, and you'd be sending everyone the same data, but at least you're explicitly saying, give everyone the same thing, or this could be make a copy of it or whatever. If we were to run this function proactively, kind of before we sent the data out, but this guy decided he didn't want it, well, we would have just run this function unnecessarily and made a copy of the data unnecessarily, because we made a copy and the guy didn't want it. So what we forced to have happen is, as part of the protocol, this guy can say when he offers the message, here's the data I would like to give you. If you want it though, you have to come back to me and ask for it.
Okay.
And then in the consume message call, we can run the function to give the copy out. So we only make the copies that we need. So that's kind of one usage or a second usage of consume message. A third has to do with what might be referred to as a two-phase commit protocol, or kind of a non-greedy protocol. Let's say we were talking about another block. Which might be a block like join block. So you can say join block of, let's say, int and string. So this join block is itself a iSource block of tuple of int and string. And basically what it does is waits asynchronously, basically it buffers up ints and strings coming in, and then as soon as it has one of each, it'll create a tuple or a tuple of the pair of those and send that off. So if I receive from this, I would receive the pair. Or if I was linked to another block, I'd be sending out these pairs. Join block can be configured to either be in a greedy mode or a non-greedy mode. So it's a source block of tuple and string, and it exposes an iTarget block as a property of int and an iTarget block of string. So I could have other blocks here. Let's say I had a buffer block of int, and he could be linked up to here, and I could have a broadcast block of string, and it could be linked up to here, and then this guy is just waiting for the right data to arrive on both pieces and sending out the tuples. Now, he can either have a buffer, an unbounded buffer internally. This is kind of non-greedy mode, where all the data will just propagate here, he'll buffer it all up, and as soon as there's at least one thing in each of these, he'll generate tuples until one of them is empty. That's the greedy approach. The non-greedy approach is, don't have these buffers, and if someone tries to offer you data, tell them, I want it eventually, but not right now. So in which case, if this guy offers a string, that string will remain here in the source. It's been offered, this guy comes back and says postponed. And in the meantime, someone else may come along and receive this data, or this guy may be linked to another block and it may try and propagate it out. Only when this guy gets data and he sends it along, does this join block now say, aha, I know that there was previously data here, now I know there's data here, now I want to consume it. But I can't just consume it directly, because if I call consume here, in the meantime, someone else may take this message, right? So if I want to be able to do it atomically across them, I engage in a protocol that's very much like transactions, where I say, could I commit this transaction if I wanted to? Once I know that everyone said yes, now I'm going to go ahead and commit it. So he'll call reserve message, I'd like to reserve this message, please. And if this guy says, sure, you've got it reserved, then he'll say, I'd like to reserve this message, please. And if this guy says, sure, you've got it, then he, without having any concerns, he can go back and consume it from both of them because he knows that no one else will have been able to take them in the meantime. And so that's the third usage of consume message is consuming previously reserved messages when you want to non-greedily consume from any number of sources that have offered you data.
Interesting. Just make sure not to greedily reserve, right?
Right.
So,
yep.
I mean, you don't want to have one of those guys just reserving everything. Like, correct? I mean, that's going to basically slow down processing.
It depends on what the block is meant to do. So you want to do whatever your semantics kind of deem important. If the join block, if these guys were just linked up to this join block, and it probably would make sense for this join block to be greedy because there's no one else who cares about this data, and it's either going to be buffered here or it's going to be buffered here, and it's more efficient to avoid that two-phase commit protocol and just take the data and run with it. However, imagine you had another join block. Maybe you had, let's say you had 3 blocks. You had 2 buffer blocks of int and 1 buffer block of string. This guy took in integers and strings. This guy took in strings and integers, and this guy is linked up in both places, right? So now this join block is able to make forward progress if there's data here and here. This join block is able to make forward progress if there's data here and here. But what happens if, let's say, a string arrives, and this guy greedily consumes it, and then an integer arrives? Well, if this guy hadn't greedily consumed it, this guy could have successfully created a tuple of both integer and string. But because this guy greedily consumed it, now we've got an integer sitting here and a string sitting here, and no one's able to pump anything out. And so that's a situation where you do want to make these guys, likely want to make these guys non-greedy, because otherwise you can end up in situations where either you've deadlocked yourself, you can't make forward progress, or at the very worst, at the very least, you've stalled yourself a little bit and have kind of put unnecessary bottlenecks into the system.
Excellent. Makes sense.
And this gets back to the comments about versus RX. These are the kinds of processing logic that would be very complicated to do in RX. And so people will do things like do this logic with Dataflow, and then once you've got your output streams, you can then process those output streams using RX.
Absolutely. Link over streams, which is link to streams.
Right.
I mean, that's continuation monad is what it really is, as Eric says. Okay.
So we've talked about action block, buffer block, broadcast block,
Yes.
join block. There's a write once block, which only accepts one piece of data ever and then always stores that data forever. There's a batch block where it's useful for doing things like turning chatty communication into chunky communication. RX has some similar operators. I forget exactly what they're called, but they allow you to basically say every n items that come through in the stream, create an array out of it, or after n seconds, create an array with what's there. It's very similar in concept. So I can create one of these batch blocks, and I can be either sending, offering data or posting data to this, and I configure this with some batch size, and every time 5 items come in, we'll send out an array of those 5 items. Because it's stateful, though, we can do other things. So, for example, we have a method on here called trigger batch. So even if he's received fewer than 5 items, you can say trigger batch, and now whatever was there will be output in array, which then allows you to build higher level things like every 1 second, no matter what's there, trigger a batch.
Okay.
Or if I have another block here, so I have a block that's sending in T's, maybe I have a block that's just sending in arbitrary signals, and every time one of these signals arrive, trigger a batch. So based on some external stimuli, take whatever I had and send it off.
Nice.
These batch blocks are also able to work in this non-greedy mode, where I could have a bunch of sources here, and I only want to consume from all of them when I have enough data from all of them to create a batch. So there's batch block. There's also the combination of batch and join. There's a batch join, which gets a little bit more complicated. But basically, instead of having an input of int and an input of string and sending out a tuple of int string, this guy also would have, for batch join block, batched join block, he would also have a batch size, so let's say 5, and his outputs are a tuple of an ilist of int and an ilist of string. So he's waiting for 5 items to arrive. He doesn't care whether they're integers or they're strings, he just needs 5 things. And then every time he gets 5, he'll create a tuple of 2 lists, one of which contained all the integers that arrived, and one of which contains all of the strings that arrived. And the sum of the counts of these two will add up to 5.
Yeah.
Trying to think, what am I missing?
But what about the type of block that sends and receives, like the propagator?
Right. So, thank you. So I'm missing an interface here, which is iPropagator block, which is both a target and a source. And in fact, iPropagator block just implements iSource and iTarget and doesn't actually add any additional methods. And all of our blocks, with the exception of action block, which is a pure target, implement iPropagator block. The only reason to have this interface is so that you can have one variable that is both a source and a target. So it doesn't actually add any additional functionality beyond that.
Okay.
So that's kind of an overall picture of the kinds of things you can do. You can create very detailed networks where you have lots of things that are forking off in different directions and coming back together. You can have circular loops. So for example, I forgot transform and transform many. You can have, so let's say you wanted to write a file downloader.
Okay.
We have a block called transform block. Let's say new transform. And there's, well, let's start with transform block. So maybe he's taking in a string representing a URL and sending out a file size. So let's say an int. So every time he's passed a URL, he's going to go off and he's going to download the URL, and then he'll return data.length or something.
Okay.
So this transform block, every time you send it a URL, he basically has 2 buffers. He's got an input buffer of strings representing the URLs, and he's got an output buffer of integers representing the lengths. And so you can hook this guy up with strings and hook him up with ints, and everything flows. But now let's say we were using a different block, which was transform many block, which is kind of like select versus select many.
Yep.
Transform versus transform many. Instead of saying length, let's say he was actually sending out parse for links. So now, every time I send him a URL, he's going to download that data, and he's going to parse it for all the HTTP links that exist there, and return an enumerable of strings. And then that enumerable of strings is basically exploded out into the individual strings, just like select many, and those strings get sent out to anyone linking, including potentially to himself. So I could say t.link to t, and now I basically have a web crawler where every time he finds a new link, he feeds it back to himself to download, feeds it back to himself to download, and so on. So you can have these circular links in the network. You can also have filters on these. So for example, I could say, I only want to link back to myself if is web page. So some function that I write that just returns true or false. And now when we linking to himself, he'll only send back to himself items that are web pages.
Exactly.
I could link to another block where I could say link to image downloader, which could be an action block or something, only if the URL is image. And so I'm building up this network where we feed back to ourselves for pages We feed to a downloader block if they're images. And then I could also even say, and if it's not a web page and it's not an image, just drop the message. So the last thing would be, if it's not a page and it's not an image, just kind of send it into the void and don't care about it. And now in a few lines of code, we have this kind of infinite web crawler, which is going to go off over the net and
Awesome.
and crawl. So the last thing to mention regarding this is another aspect of how this integrates with the async language support.
Okay.
Which is, I talked about how you can kind of await receiving from a block, or you can await the completion task, but you can also use async and await inside of one of these blocks. So action block, transform, many block, they all accept either synchronous delegates or in effect asynchronous delegates. So here I could say async, meaning I'm writing an asynchronous method, and then instead of calling download, I could call download async, and I could stick here my
Good old await.
await. And now, if I have this download async method, everything behaves exactly as before, except we're going to release the thread while we're waiting for this asynchronous processing to complete. And yet all the additional functionality on the block, for example, how much concurrency you want to allow, which schedulers things go to, and so on, all remains.
Excellent.
Yeah. So that's sort of I realize, a very, very fast tour.
But that's really good. A very, very clear tour as usual.
Thanks.
So thank you. So before we leave, I mean, what's next? I mean, you mentioned you've seen people actually use this in the real world. You're seeing them use Link and this, or RX and this in the real world. What kind of feedback have you gotten? I mean, the async keyword's been out for a while.
Yeah. So far, it's been, you're referring to Dataflow and the
Dataflow
async,
and this, all of this, because it's all related.
Yeah, the async language support, the feedback has been phenomenal.
Okay.
It's, there have been some good nitpicky things here and there. We don't like how things are named, or we'd like to see more things as interfaces, or we'd like to see slightly different behavior in terms of how things post back, or we want more control, and so on. All great feedback, and we want to see it come, more feedback come in. But the high level message has been, this makes things so much easier than they were in the past. This is awesome.
Absolutely.
So that's been great. On the Dataflow side of things, we haven't had as much pickup as the thousands and thousands of people that have picked up the language support, but what we have seen has also been very positive. Just even from people using one or two of the blocks, just the action block eliminates a huge amount of boilerplate code that you would otherwise have to write yourself. And then there are just a large number of problems, both inside Microsoft and outside of Microsoft, that map to these kinds of pipelines or actor models, where people have started picking up these types, and they really like how it simplifies the code. Again, we've gotten some good feedback, things like make these interfaces co and contravariant, reduce the number of allocations that you have, which is something we're striving for right now, to get them as close to zero as possible. We'd like to see more blocks that do specialized things. But for the most part, so far it's been very positive. So we just, unfortunately, a lot of that communication has been kind of in email. So we just put up a dedicated forum for TPL Dataflow, which you can find off of the DevLab site. And you can start providing feedback so that the masses can see it there as well.
That's a good point. I mean, DevLabs is your chance to really impact the direction of the project, because in some sense, DevLabs is really a synonym for incubation. In some sense, I mean, further along the lines, because if you look at RX, is no longer on DevLabs. It's now in a real data center,
right?
Like a data development center.
Yeah, exactly.
Yes, which is congratulations to those guys.
Yeah, it's awesome.
But this is cool because you got there. This is the front lines. People can help you do the right thing, and this looks really nice.
Yeah, and I would say this is definitely beyond incubation.
Yes.
It's something we're doing, but at the same time, we're still at a point where we can influence what things look like and what functionality we have. And so the more feedback we get, literally now, the better.
Awesome. Hey, thanks for coming on C9, man. It's always great to see you.
Thank you, Charles.
And we'll come visit you again.
Please do.
Cheers.